Alright, so today we're going to be talking about geometric sequences, which is 5-3. So we've talked about arithmetic sequences, we've talked about arithmetic series, and now we're moving on to geometric sequences. And the last set of notes will be geometric series. So let's talk about what this means. So we've talked about sequences before, and these are a set of numbers that go in order, and they have a pattern. Okay, that's what we know a definition of a sequence is. So a geometric sequence is a sequence that has a specific type of pattern, and the pattern of a geometric sequence is defined by you're always multiplying that number by a certain number, so you're always multiplying by the same number to get to the next. Now, you can also multiply by a fraction, like 1/2, which is going to appear like you're dividing. So it's multiplication and division. Okay, that's what defines a geometric sequence, is we're either multiplying or dividing each term. Now, just like with arithmetic sequences, geometric sequences can be written either explicitly or recursively. This is the explicit formula, and the recursive formula is only useful to find a term after the term you have or a term before the term you have. Explicit rule works to find any term in the sequence. Now, the main difference that you're going to notice about the explicit rule or the explicit formula compared to the arithmetic is that there's no d. Okay, so there's no common difference because we're not subtracting or adding. We're now dividing or multiplying. And this is called what we call the common ratio. The common ratio is what we either multiply or divide by each time. Okay, so that's what we call the common ratio. And it's denoted by the letter R. So the first question just says to find the common geometric ratio of the terms 2, 4, 6, I'm counting even numbers, 2, 4, 8, and 16. So what do you notice as we go from 2 to 4? Good, and then you can confirm that because we also multiplied by 2 to get from 4 to 8, right? So you can see that pattern, and that would mean that your R value is equal to 2. So that's how you find the common ratio. You figure out what you multiplied by each time. Now, this question doesn't say to find anything else, so that's really all you have to do here. It just wants to know what's the common geometric ratio, and the answer here is 2. So does anybody have any questions about why it's 2? Okay. So now we're going to look at a few different examples, and we're going to determine if the given sequence is geometric, and if it is, we're going to identify the common ratio. Okay? So in this case, not all of these are necessarily geometric. We have to determine whether or not they are, and if they are, we're going to identify what the common ratio is. So in the first case, what do you think, geometric or not? Geometric. Yes, it is geometric. And why is it geometric? Good. We're multiplying by 2 each time. Good job. So in this case, yes, it is a geometric sequence, and we know that because it has a common ratio. So it's not enough to just check if the first number you can multiply by something. You have to at least check the next term, because what can happen is you could see that you went from 3 to 6 and think you multiplied by 2, but then say the next term goes to 10 or something. So you always have to check at least the next set to make sure that it's really being multiplied by 2 every time. Now let's go ahead and try C, because we're already zoomed in over here. So to get from 1 to 5, what would I multiply 1 by? 5. So that would have to stay true for the next term. To get from 5 to 9, did I multiply by 5? No. So what do you think? Is this geometric? No, it's not geometric. It may have a pattern. I don't know what the pattern is. It looks like it's being added by 4 each time, right? You guys see that? So this is a sequence that has a pattern, but it's actually arithmetic, okay? So you can say no, and you can say arithmetic if you want. And this arithmetic sequence has a d value of what? 4. So yes, it is a sequence, but it's not geometric. Does that make sense to everybody so far? All right. So let's go ahead and look at B and D. So for letter B, we go from 3 to -9. And to do that, we would multiply by what? Good, -3. And let's confirm if that's the case for the next term. So to go from -9 to 27, what would you multiply by? negative 3. And to go from 27 to negative 81, you would also multiply by negative 3. So would you say that this is geometric? Yes. And what would be my common ratio? Negative 3. So something to always note when you're dealing with geometric sequences. If you have a negative common ratio, what do you notice happens with the terms? Yeah, exactly, good. It alternates. So it goes from positive to negative to positive to negative. And that will always happen if you have a negative common ratio, because you're going to multiply a negative by a negative. That's going to become a positive, positive, negative, and so on. It's just going to keep alternating. Okay, so that's another thing to look out for. And moving on to D. So you can also think of division. So this may help you. What could I divide 48 by to get me to negative 12? Good, negative 4, right? I could divide it by negative 4. And would that also ring true for going from negative 12 to 3? Would that also be division by negative 4? Good. So when you have to divide, when you're going downward, okay, we always want to write our common ratio as a product, not a quotient, okay? So, yes, it is a geometric sequence. But if you divide it by something to get the common ratio, you're actually going to write it as negative 1/4. Because dividing something by negative 4 is the same thing as multiplying it by negative 1/4. Everybody understand that? Okay. So you just have to know, to rewrite it as a fraction. So if your geometric sequence is going downward, as if it's descending, it's always going to be a fraction or a decimal. It's never going to be a number that's larger than 1. It's always going to be smaller than 1 because that's the only way you can multiply by something that gives you a smaller number. Does that make sense? All right. Let's go ahead and move on to our next example. So this one says to analyze the geometric sequences and state the indicated term of the geometric sequence. So in this case, they want us to find the sixth term of, and they give us a few terms. And the first thing we're going to do if we want to write an explicit formula, which we're going to have to do here, is to find our first term. And what would our first term be? Good. Once you've identified the first term, you're going to want to find the common ratio. What do you think the common ratio is here? Good. Multiply by negative 5. So to get from 3 to negative 15, you would multiply it by negative 5. To get from negative 15 to positive 75, you would multiply by negative 5. Everybody understand that? Now, say it's a decimal and it's hard to just identify by, seeing it. You can take negative 15, divide it by 3, and you get negative 5. That's also a way to find it. And then you could take 75, divide it by negative 15, and you would also get negative 5. So you can always check your work by just doing the division as well. Now that we have A1 and R, we're going to go ahead and write our explicit formula. So the formula for the explicit formula for a geometric sequence is A sub n is equal to A sub 1. Make sure I got it. I get paranoid about it. Yeah, here we go. Yep, I was right. Times r to the n minus 1 power. Okay? So that's the general formula, and we're going to plug into this formula. So A sub n is equal to your first term times. Now, this is really important. If your r value is negative, you need to put it in parentheses. If you want to write yourself a little note, whatever you got to do to remember that, if your r value is negative, okay, you got to put it in parentheses, okay? Very important. That could mess up your whole equation because it just throws off the whole multiplication, all right, the order of operations. So now that we have the general formula for the explicit formula, what are we going to be plugging in for n here? 6, because we're looking for the sixth term. So I'm going to be plugging in 6 for n. So it's going to be a sub n is equal to, or a sub 6 is equal to 3 times negative 5 to the 6 minus 1, which means a sub n, and for these geometric problems, these numbers are going to get big really fast, so you're probably going to have to use a calculator here. Yeah, so this number is very big, and it is negative 9,375. So in my calculator, I just put in negative 5 to the 5th power times 3. That's how I got my answer. Now you're going to notice that with these geometric problems, your numbers are either going to get really, really big or really, really small, really fast compared to arithmetic. Anybody have a hypothesis on why this is the case? Good. Yeah, so if I told you you have a job and I said you're going to get a raise, an incremental raise, and I said we can either add $2 to your salary every week or I can multiply your salary by 2 every week, which one are you going to go with? Multiplication, right? And as you multiply by 2 every week, your salary is going to get really big. It's going to get exponentially bigger, right? Because the number you're multiplying by is being multiplied by 2 again. It's just getting very big. So the important thing to note here is geometric sequences actually model exponential functions. And arithmetic sequences, anybody know what they model? Linear. Good, they model linear functions because they only go up by a set amount each time. So that's just something to think about. Let's go ahead and try B. All right, so for B, the first thing you're going to do is you're going to identify the first term, which is 64. And the next thing you're going to do is identify your common ratio. Now in this case, are my numbers descending or ascending? Descending. So my common ratio is going to be a fraction, or you could put it as a decimal. Now, it's going to be a negative because it's going to a negative, right? And what would I divide 64 by to get to 32? 2. So my common ratio here is negative 1/2. So if you multiply 64 by negative 1/2, that's the same thing as dividing it by 2, and that gives you negative 32. And if you multiply negative 32 by negative 1/2, you would get 16. So if you're not sure, always check in your calculator. And you can put in negative 1/2 is negative 0.5 in the calculator. So now that we have our A1 and our common ratio, which could also have been written as negative 0.5, A sub n is equal to my first term times my common ratio, which I'm putting in parentheses because it's negative, very important, to the n minus 1 power. And now that I have the general formula, I'm ready to plug in as needed. So what am I going to be plugging in for n here? 11. Good. So it's going to be A sub 11, the 11th term, is equal to 64 times negative 1/2 to the 10th power, because 11 minus 1. Everybody see how I got that? Now, you could put in negative 1.5 in the calculator, put it to the 10th power, and you're going to get a really small decimal. I'm going to leave it as a fraction, and you'll see why. So this comes out to be, now if you want to square a fraction, you square the numerator and then you square the denominator. But anything that's negative to an even power is going to become what? Anyone know? Positive. Good. So 1 to the 10th power is just 1. And then 2 to the 10th power, I don't know, the calculator will tell me, is 1,024. And it's positive because it's to an even exponent. Now, when you're multiplying a number and a fraction, you just multiply straight across. This is over 1. So 64 times 1 is just 64. And 1,024, because 1 times 1,024 is 1,024. Now we're trying to reduce this fraction. I'm going to just give you, the answer here. This fraction is reducible by dividing the numerator and denominator by 64. And when you do that, you get 1 over 16. So 1 over 16 is the 11th term of this sequence. So as you can see, it's going down pretty fast, right? It's starting at 64, and 11 terms in, we're already at 1/16. So exponential growth and exponential decay. This is exponential decay. Any questions so far? All right. So the next one we're going to do is our missing term question. So you remember these back from when we did arithmetic, but the procedure is a little bit different for these, okay? So let's talk through the steps. So it says state the missing terms in the geometric sequence. So the first thing I want you to do is take the number on the right and divide that number by the number on the left. Now, the calculator, once again, will give you a decimal, but it's a little bit easier to keep it as a fraction, which you'll see. So, if we have it as a fraction, we're going to try to reduce this fraction. Any ideas on what these are both divisible by? 5. So, I divide the numerator and the denominator by 5. And I get 16 over 9. I'm going to actually write it here so we have a little more space. You'll see why. So we're not done yet. We have another step. Now, this step is similar to arithmetic. You take the number of spaces plus 1. How many spaces are there? 1. And then 1 plus 1 is? 2. That number, instead of dividing by it, it's the root that you take of it. So you're taking the second root of this. That's where you get the root from. How many spaces plus 1 gives you your root, okay? Now, in this case, anybody know what a second root is? It's just a regular what? Square root. Yeah, it's just a regular square root. Second root is just a regular one. If you get 3 or 4, that's a different one. Now, anybody remember what the square root of 16 is? Good, and the square root of 9? 3. So once we've done that, we now just found our common ratio. So now that we found our common ratio, to get the next number in our sequence, we take our first term and multiply it by 4 over 3. So the easiest way to do this is just take 45, multiply it by 4, and then divide it by 3. And when you do that in the calculator, when you multiply 45 by 4 over 3, you would get 60. And that would be your blank. And to check that you did it correctly, you can take 60 and again multiply it by 4 over 3, and you should get 80. And that's how you know you've done it correctly. So do I have any questions about example 6a? All right, let's move on to example 6b. So in this case, we have a little bit more blanks to fill in, right? A few more. So you're going to take the number on the right, divide it by the number on the left. In this case, is it decreasing or increasing? Decreasing. So we know that our fraction is going to be less than 1. So you're going to try to simplify this fraction, and I'll just tell you that they're both divisible by 12. And when you divide them both by 12, you're going to get 1 over 81. So I'll write it out here so we have some space. Now you're going to take some root of this, but how do I figure out what root I'm going to take? Good, spaces plus 1. So if I have 3 spaces, what root am I going to take? The 4th root plus 1. So I'm taking the 4th root of this fraction. The easiest way to take any root of any fraction is to do the numerator and denominator separately. So the 4th root of 1 is just 1. 1 is always just 1. Remembering back to your days of doing roots, we know that 81 breaks up into what? 9. Good, 9 and 9. And 9s break up into what? 3 and 3. And we're looking for groupings of what size? 4. Groupings of 4 because it's the fourth root. So do we have a perfect fourth root here? Yes, we have a perfect fourth root and it's 3. The fourth root of 81 is 3. So if it helps to keep your mind at ease, taking the fourth root of something is like taking the square root of it twice. What's the square root of 81? It's the square root of 9. 3. So this is our common ratio. Now that we have our common ratio, we're going to multiply it by our first term here. So multiplying by 1/3 is the same thing as doing what? Dividing by 3. So when I divide 972 by 3, I get 324. I'm then going to divide 324 by 3 again, which gives me 108. And I divide by 3 again, and I get 36. And what is 36 divided by 3? 12, which is what we wanted, right? So that's how you get your blanks. Any questions about this? Make sense? Alright, so the next two problems we're going to do are going to be writing the explicit formulas and then getting the first 5 terms. So in this case, they already gave you A1 and R. So your formula is AN is equal to the first term times your common ratio. I just like to put it in parentheses anyways, just makes my life easier, to the n minus 1 power. Everybody understand how I got that? Now we're going to find the first 5 terms. You could use the formula to do this, or you can just use the common ratio. Are these numbers going to be decreasing or increasing? Decreasing. Basically, we're going to be dividing the numbers by what? 3. So what's 12 divided by 3? 4. So the second term's got to be 4. Now for the third term, is 4 divisible by 3? No, so it's just 4 over 3. So 4/3 is also not divisible by 3. Easiest way to divide a fraction by a number is to multiply it by what you're dividing by the denominator. So 4/3 divided by 3 is actually just 4/9. And the fifth term would be 4/9 divided by 3, which is 4/27. So the formula would also generate this, but it's also easier to do it this way in my opinion. So those would be our first 5 terms. So we're just multiplying by 1/3 each time. Questions? Okay. Now we're going to look at this one. Now, in my opinion, I think it's easier to work with fractions than decimals in this case. You can use the decimal if you want, but the problem is when your decimals get really small, what happens is they get like this, 0.00005 or something, and then you got a ton of zeros to write. So it's sometimes easier to just keep it as a fraction, okay? But, you know, you do what you got to do. Just keep in mind that answers can be written differently on tests. So 0.2 is the same thing as 2 over 10, which is the same thing as what? 1/5. So I'm going to use 1/5 as my common ratio, which is the same thing as 0.2. So if you do 1 divided by 5 in your calculator, I promise it is 0.2. So that's what I'm going to be using to write my formula. So my formula is A sub n is equal to my first term times my common ratio to the n minus 1 power. Now once again, like I mentioned earlier, you're welcome to use that formula to calculate the next term by plugging in for n, but I think it's easier to just use the common ratio. So if you're multiplying something by 1/5, it's the same thing as dividing it by 5. So 5 divided by 5 is 1. So the next term after 5, because 5 divided by 5 is 1. Now 1, we're taking this term and dividing it by 5. 1 is not divisible by 5, so it's just 1/5. 1/5 is not divisible by 5. When you divide it by 5, it's 1/25. And 1/25 divided by 5 is 1/125. So as you can see, the numbers get really, really small. Really small. And you could have done this with the decimal as well, and it would still work. You'd be basically multiplying, you would just be multiplying 5 by 0.2 each time. And you'd get smaller and smaller decimals. Now keep in mind, oh my gosh. Now keep in mind that if you decide to use the decimal, you're not going to be dividing by that decimal. You're going to be multiplying by it, okay? So if you use the decimal, you still multiply, always. If you divide by a decimal that's smaller than 1, your number gets bigger. So make sure you multiply. Alright, moving on. We're going to look at these word problems. So it says, when radioactive substances decay, the amount forms a geometric sequence when measured over constant intervals of time. The table shows the highly radioactive element, admesium, decaying over a 2-hour period. It's not admesium, it's adamcium. Adamcium? Determine the amount of whatever that would be left for each hour after it's initially started decaying. So basically you started with 1,320 grams of the substance at hour 0, and we don't know how much you had at hour 1, but you knew at hour 2 you were left with 384. So imagine you're in like a chemistry lab, and you're supposed to check on your substance after an hour, but you forgot. So you're at 2 hours. So now you have to use math to backtrack what you missed, basically. So how we do this is just like we did the other problems with the gaps, okay? We have our first term here, and we have the third term. So we're going to take the further term, and we're going to divide it by the first term, just like we did earlier. So in this case, this is radioactive decay, meaning that the amount of the substance is going down over time. So in this case, we have this number, and we want to see if we can reduce it. And I checked earlier so that we don't spend a lot of time, but it's divisible by 24 on the numerator and denominator. And when we divide it by 24, we get 16 over just a minute, I typed it in wrong. 55. Now to find the common ratio, you're going to take the root of how many spaces we have between those two. How many spaces were there between these two? 1. So you're going to add 1 to that, so you're taking what root? Yeah, just the regular square root. Now in this case, 16 is a perfect square, but is 55? No, so we're just going to go with the decimal on this one to make our lives easier, okay? So I'm going to do in my calculator 16 divided by 55, and I get a decimal, and I'm going to square root that decimal. And when I do that, I end up with, and I'm going to leave it to the thousands place, 0.539. So I'm leaving 3 decimal places just to make it as accurate as you know, not as accurate as possible, but pretty accurate. If you only go 1 decimal, it's not going to be that accurate. So this is our common ratio. So now that we have that amount, we are going to multiply this number by it. So 1,320 times 0.539 comes out to be approximately Everybody who tried it get that? Now, how would I get the third value? The third hour? Good. You would multiply 384 by the common ratio. And when you do that math, you should get approximately 207. And then to get the next value, I would then do what? Multiply it again. And you should get around 112. So basically, after 4 hours, your substance that was once 1,320 grams is now 112 grams. Okay, that's what radioactive decay is. Any questions on that? All right, let's go ahead and try one regarding bouncing balls. So if you think of how a ball bounces, think of like if you're in gym class and somebody throws kind of bounces a ball on the ground. You notice the ball will go up a little, and then what do you notice happens as it keeps going, bouncing along? What do you notice about the height of the bounces as the ball kind of goes this way? They get shorter, right? That's another form of exponential decay. So that actually happens in a very scientific way, that it actually depreciates, okay? So we want to find the missing heights of the bounces. So as you can see, this is decay. It's going down. So you're going to take your further number, which we have 49, divide it by 100. And we're going to go with decimals on this one. So with the real world problems, it's sometimes just better to use decimals because they're not going to come out to be nice numbers. So if I do 49 divided by 100, that's just 0.49, 0.49. And then I need to then divide this number by what? Oh wait, not divide. Oh my gosh, sorry. I'm like thinking of arithmetic. I need to take what root of this number? 2. Good, the second root. Because there's only one space between 100 and 49. And the square root of that is actually 0.7. So this is my common ratio. So how would I get from 100 to my next bounce? What would I do with the 100?
Multiply it by 0.7.
Good, I'm going to multiply it by 0.7, which gives me 70. So this one's height is 70 centimeters. And now that we know what the common ratio is, how can I find the bounce after 49? Good, I multiply it by 0.7, which gives me 34.3 centimeters. And then, once again, I'm going to multiply by 0.7 to get the last one, which gives me 24.01 centimeters. So you could keep going until the ball basically just stops moving, right? You know at the very end, when you like dribble a ball, like it has those like really tight like micro bounces. That's like what's happening here. It's got to bounce out until it hits 0, basically. So that's kind of how that works. It's interesting to kind of see how it applies to real life. You guys have a little bit of time before lunch, and then you guys have the rest of the second period for work.